if you need that then. Okay, so what we want to look at tonight to begin with is what we mean by a subtended arc and how to find a arc length like this. And I'm going to derive the formula for you, but I'm not going to do that yet. I think I wanted to do that on the next page here. So I'm just going to give you the formula. So if you have a circle, this is called a central angle. That's the radius. S is what we use to represent the arc. That's just a piece of the circle. So the formula is this. You want to write this down because you will use this. Is S is equal to R theta. So all you do is just multiply theta times R, and then you get the length of the arc. But this is what's real important, is theta must be in radians. If it's not in radians, you get ridiculous answers. And let me show you what I mean by that, okay? I'm going to draw a circle. This is worth writing down just as a note to yourself. Let's say that that is 5 centimeters, and let's say you have a 90-degree angle, okay? If you want to find the length of this arc, which is that part of the circle right here, I'm going to do this wrong on purpose, and you tell me if this is what I'm doing wrong. Okay, if I just do the radius, which is 5 centimeters, times 90, which is the angle, I would get 450 centimeters, okay? What do you guys think? If that's 5, don't you think 450 is a tad bit big? Okay, it's not a tad big, it's way big, okay? So don't make that mistake. That 90 degrees has to go to radians, then you're going to get a sensible answer. Okay, everybody got that? Okay, so it's real easy to find the arc length, but just make sure that you change your angle. So I'm going to do this. Okay, remember we learned how to change to radians last time. What do you multiply by to change to radians? Pi over 180, right? Okay, and you can reduce the fraction, which reduces to 1/2, so that's pi over 2. Okay, so the correct way to do this problem then would be S is equal to the radius, which is 5 centimeters, times pi over 2. Then you would just take your calculator and do that, and you would get a lot more sensible answer. I always like to kind of show that, because a lot of times students get answers that are way wrong, and they don't catch that. So you want to think about whether your answer makes any sense. So I'm just going to go now 5 times pi over 2, and then that would give about 7.8 or 7.9, or I'll just say 7.85 centimeters. Is that a better and more logical answer? What do you think?
Yeah.
Yeah, okay, if that's 5, it makes sense that that's a little bigger than 5, all right? So that's how you work with finding an arc length. Just make sure that your angle is in radians, okay? Okay, we're going to do a couple of these just together. I'm going to do one and then let you do number 20. Now this one I'm not giving you a picture on, but we're going to find the arc, so we're going to use S equals R theta, okay? So the big question on this is my angle in radians? What do you think? Yeah, and you know why? Because it doesn't have a degree symbol, okay? If it doesn't have a degree symbol, it's radians, okay? Same thing with problem number 20, that is in radians. Not because it has a pi, it's because it does not have a degree symbol on it. So what that means in this problem, all you're going to do is you're going to just take the radius, 18.15 centimeters, and then you're going to multiply by 2.50 radians, okay? And then this would be one that we just take the calculator out on and crunch it out, and then we'll have the length of the arc, okay? So this is a real simple thing to do if you're already in radians. It doesn't take much work at all. So I'll do that, and I'm just going to leave the answer the way it is. Just leave all the decimals, so that's 45.375 centimeters like that. Problem done. Okay, everybody got that? Okay, S equals R theta. Okay, do the next one. Get your calculator out, just do that, and see if you get a good answer on that. Again, theta is already in radians, so it should be a simple matter of just using your calculator, okay? And if you have to round, you'll have to round on this. Just round to like 2 decimals. Like my math lab, they're always going to tell you what to round to, okay? And you can pretty well do this in one step on the calculator when you do it. Okay, now what I usually do is just get the numerator. I just go straight across and then divide by 3, and then that'll give the answer. Okay? So most of this you're going to have to use your calculator on to get a decimal answer. So let's just take that as 13.19 meters as the answer to the problem. Okay? Okay, so that should be a real simple thing for everybody to do. Okay? But if I give you a degree measure, tell me what you do. Convert it to radians, then you use S equals R theta. Okay, so be cautious about that. Okay, any questions? Okay, all right. This next one, we don't have to do this. I've already done enough with this, I think. So that one is 0.934 millimeters. And then that's already in radians. So you do that, go ahead and just take your calculator and crunch that out. And let's see if we all get the same thing on this one then. Everything I gave you was already in radians, so that makes it pretty easy. Okay, so here's what I'm getting. 5.28 millimeters is what I'm getting. Does that look okay? Okay, all right. Okay, now what I'm going to do next is I'm going to show you where the formula comes from. So the higher you get in math, the more your teachers are going to prove things and derive things and show you where they come from. So somebody had to figure this out. I'm going to show you how we figured out this formula. So what I'm going to do is I want you to just draw a circle kind of at the side so we can represent our variables correctly. And let's put like, there's the center of the circle. That would be the radius. And then let's draw another radius. And then that would be theta. We're going to use theta. And then this right here is S. So we always use S to represent the length of the arc. Okay, like that. Okay, so what I'm going to do is I'm going to show you how you use a proportion to build this formula. The formula pops out of this proportion real easily. So what we're doing is we're doing a part and we're relating it to the whole. Okay, so here's the idea. All right, real simple. The part would be the arc, right? What do you call the distance all the way around the circle? The circumference. So we're going to relate the length of the arc to the circumference, okay? Now what we're going to do is the central angle, okay? So what is the angle all the way around the circle? It's either 360 or 2 pi. We're going to use 2 pi because we want to be in radians, okay? So what I'm doing is doing the central angle over 2 pi. So again, I'm doing the length of the arc related to the whole circle, the angle related to the whole circle. Does that make sense? It's part to whole. So let's write down what we have and then we'll solve it and the formula will pop out of here. Well, the arc length is S, so we're going to do that. Okay? Do you guys know from your background what the formula for a circumference of a circle is? It has pi in it. 2 pi r. Okay? Pi r squared is the area. Okay? So what I'm going to do there is I'm going to put 2 pi r like that. Okay? Now when I go to this other part, okay, the central angle is theta. And then remember, all the way around the circle's 2 pi. So if you solve that equation for S equals r theta will pop out. Okay? So probably the most likely way you've learned how to solve an equation like this is to cross multiply. So we can multiply those two things together, and then we can go this way and multiply those two things together like that. So when we do that, we're going to have S times 2 pi is equal to 2 pi r times theta like that. Okay? Now, I want you to do one more step and then we're done. So if you want to get S by itself, what do you do to both sides of that equation? You divide by 2 pi, right? You want that to go away. So you're just solving an equation. So let's do that and let's see what pops out of this stuff. So I'm going to divide by 2 pi, divide by 2 pi. You see how it works? These cross out, don't they? So the 2 pi's cross out, so you're left with S equals r theta. Isn't that cool? That's how we figure this out, okay? Just with a little bit of logic and a mathematical proportion. So again, you end up with S equals r theta. Okay, that's where that formula comes from. That's one way to derive that for students, okay? All right, is that sensible what I did? Tell me if that makes sense to you. Okay, we're going to do another formula in a similar way. Proportions a lot of times are very useful when you're dealing with geometric concepts. Okay, I don't have you ever do that on a test or anything, but I like to show you that in class and just tell that where that comes from. Okay, the last thing that we're going to do on this part of the notes is what we call an area of a sector. So what you're looking at, is you're looking at like a part of the circle. That's called a sector. It's kind of like a piece of pizza or a piece of pie or something. So what we're going to do is find the area of that, and we're going to do like a derivation of this thing also. So the formula that you get is this. It's the area is 1/2 r squared theta. And again, theta has to be in radians. I've already typed that out for you, okay, like that. So I'm going to derive that formula for you also, and then we're just going to do a couple of problems on this. So this is a simple thing to do. If I give you a radius and an angle, then it's pretty easy to find the area of that sector, okay? So again, what we're going to do is we're going to do a part to whole proportion. So I'm going to set this up like this. That's the radius. That's theta, that's S, and then we're looking at trying to develop a formula for the area of that sector, okay? That's what that's going to be then, okay? All right, so we're going to do a part to whole proportion on this now. So we're going to do this. First thing we're going to do is we're going to look at the area of the sector, and I'm going to use A on that, okay? So we're going to have A. All right, remember, we're looking at the whole, okay? So that's the part of the circle. The whole would be the area of the whole circle. You guys know the formula in your background for area of a circle. Pi r squared, right. So we're going to put A over pi r squared. That way we've got the area of the sector related to the area of the entire circle like that. So you got to know that formula to put this together, okay? Now we're going to do the central angle. The central angle is theta, so I'm going to put that like that. Okay, and let's see, we've got that. All right, so that's going to be theta, and then all the way around the circle is going to be 2 pi like that then. Okay, so what I'm doing is there's more than one way to do this. I'm doing the sector related to the whole circle, the central angle, and then the whole angle is 2 pi, right? Does that make sense? Okay, part to whole. Now go ahead and cross multiply it. We're going to solve it, and we're going to see if that formula doesn't pop right out of this then. Okay, I did this today in another class, and I did it a different way. This is probably the simplest way to do this. So we can cross multiply. So you would have A times 2 pi, like that. Then you go the other way. It doesn't matter what order you put them in. We would have theta times pi r squared like that, okay? Now, what do you do to finish it up? If you want to get A by itself, what do you do to both sides of the equation? Divide by 2 pi, good. Okay, so we're going to do that. Divide both sides by 2 pi, and then that's going to give the formula. So notice what happens is the pi's cross out, so you're left with theta r squared over 2. And you can write the formula that way if you want to, or you can write it as 1/2 r squared theta. That's just the most common way that we write that like that, okay? So you'll see the textbook write the formula that way. Doesn't matter what order you multiply those in, but the key thing is theta has to be in radians or you'll get ridiculous answers, okay? You guys follow what I did there, okay? Okay, so that's where that comes from. And we knew about areas of circles and circumferences before we had the concept of radian measure. We had to know about pi before we could develop the concept of radian measure. Okay, so what we're going to do with this is I'm giving you theta and r. That's all it takes to find the area of a sector. Let's actually draw a little picture on this too. So let's put a circle, and let's say that we have a radius of 10 inches, okay? I'm just kind of curious if you know what two radians is. That's 2 radians, right? Okay, it's already in radians. What is halfway around the circle in radians? Pi. You want to know that, okay? And pi is 3.14, so that angle's probably somewhere kind of like that. I want you to know that 3.14 would be 180 degrees. That's less than 180 because it's less than pi. So what we're going to do is we're just going to sketch this. Doesn't have to be perfectly accurate, so we have that. And what you're doing is you're looking for the area of that sector. Okay, that's what we're going to crunch out. Okay, so again, we just write down the formula, which is area is 1/2 r squared theta, and we just work out the details. Okay, so the radius is 10 inches, so we're going to put that in, and then we're going to square it. We're already in radians, so we just do that. Okay, now this problem, I would hope that you wouldn't get your calculator out, although I see students go all the time. What happens to the 2? They cancel. You can cancel the 2's out, so what's the answer to the problem? It's 100. Okay, what are the units? Square. Okay, hopefully you know that when you're doing area, that's always in square units, because you're squaring those inches. Okay, so what you would end up having is that's going to cross out, so the area of that sector would be 100 square inches like that. That's it. Okay, so that one's pretty simple to do without a calculator. All right. Okay, I'm going to let you guys do 24, and then we'll do 25 together, and then we're going to start the last part of this section. So go ahead and take a couple of minutes to do this. You can write down the formula, 1/2 pi r squared. Okay, I gave you theta is 90 degrees, and I gave you the radius is 4. That's all it takes to know the area of that sector. And I'm also going to draw a picture on this too. That's worth doing too, but you don't have to. What's the first thing you have to do on this problem?
You have to make it radians.
Yeah, you got to change the 90 degrees to radians, right? Okay, so you have to do that. Otherwise, your answer isn't going to make any sense. So what's 90 degrees in radians? Pi over 2. Okay, all right. And it's easy to check that too, because remember pi is 180, so 180 over 2 is 90. Okay, so that's how you have to start. And then go ahead and plug it in, and let's see what we're doing. You're going to need your calculator on this one too. So we have 1/2 pi. Whoops, I have the wrong formula on there. That needs to be 1/2 r squared theta. So that was not right. Okay, so let's see. If I do that, we'll have 4 centimeters squared, and then times pi over 2. Now, like when you're doing your homework, sometimes on my math lab, they'll say leave pi in the answer, and then sometimes they'll say get a decimal and round. I'm just going to do both on this one. So that's going to be 1/2. 4 squared is 16 square centimeters. Then that's pi over 2 like that. Okay, if you multiplied straight across, you would have 16 pi square centimeters, and then 2 times 2 is 4. So the exact answer, you can do 16 over 4 and get 4. So that's an okay answer if I want pi in the answer, okay? If I want you to get decimals, just do 4 and then multiply it by pi, and then we'll round that off. So if you round that off, that's about 12.57. I'm getting like 566376061. So we got that then, okay? All right. Students usually don't have much trouble doing this kind of thing. Is that how you feel? I mean, if you know the formula, then it's not going to be that hard of a thing as long as you can use your calculator and perform the arithmetic, okay? All right? Okay, this next one is just kind of doing the problem in a different order. Okay, so we're going to find theta this time, and then this time I give you the area of the sector. I give that in square inches, and I give the radius is 2.5 inches. Okay, so again, it's going to be the same formula, so you want to start by just writing down the formula. Now, what I'm going to do on this, now you can go ahead and plug your numbers in now, or you can solve for theta now, which is what I'm going to choose to do on this. So what I'm going to do is I want theta to be by itself. Okay, so here's what I'm going to do. If I want the 2 to go away, then I can multiply by 2 to make it go away, because I want theta by itself. So I would have to do that to both sides of the equation. Multiplying by 2 would get rid of that fraction. The other thing is I want r squared to go away. So what I can do there is I can really just divide by r squared to get that to go away. So I'd have to do the same thing over there then. Okay, so what I'm doing really is I'm multiplying by 2 to get rid of the 2, and then dividing by r squared to get rid of r squared. So I would end up with this. I would have theta is equal to 2a over r squared. Okay, does that make sense? That's basic algebra, so you got to get rid of the numbers that are attached to that theta, multiply by 2 and divide by r squared is one way to do that. Now what I'm going to do is just plug everything in. So the area was given as 10 square inches. It's a good idea to put your units in to see how this works out. And then your radius is, you got to square that radius, so you would have 2.5 inches squared like that. So I'm just plugging in the area, which is given, and the radius, which is given also like that. Okay, and that's what theta is going to be. So now what I'm going to do is just calculate this out. So the numerator is 2 times 10 is 20 square inches. Okay, you can take your calculator and square 2.5. If you square 2.5, that will give 6.25, and that's going to be in square inches. Okay, then I'm just going to take the calculator and I'm going to divide those two numbers then. Okay. All right, so again, if I do 2.5 squared, I've already done that, so that will give you the 6.25. So I'm going to take 20 divided by 6.25, and then I'll round this off. So that should give theta is equal to 3.2. Okay, now, one thing I want to talk about, the reason I want the units in there is what happens to the inches squared. They cancel, right? So you just got 3.2. Now, that is radians. You don't have to write radians on there, but it's a real number. Radians is not technically a unit. It's just the concept of what that answer is. So you can leave it there, or you can write radians. Okay? When those things cancel out, you just need to know that you're going to get a number, but that will be in radian measure. Okay? So that's how that goes. Okay, you guys feel okay with what I'm doing so far tonight? Okay? All right, we haven't done the most challenging part yet. That's what comes next, because what we do is we've learned about angles, which is important in trigonometry. Now we're going to do a little bit with this. We're going to do a little lesson in physics. So this third part that I gave you of this handout has what we call angular and linear velocity. So this is the part that you got to work the most on. Okay? So to begin with this idea, first thing I'm going to introduce you to is what we mean by angular velocity. Okay, if you're not familiar with that topic, well, every time you drive in a car, angular velocity is coming out on this thing, which is called a tachometer. Most cars have a speedometer and a tachometer on it, and the tachometer is measuring angular velocity. So what it's doing is it's doing this. RPM, what does RPM stand for? Revolutions per minute, okay? So your engine turns in a circle real fast around the crankshaft and everything. So if you rev up your engine to 4, that doesn't mean 4 revolutions per minute because the engine wouldn't have much power. It's actually 4,000, okay? So this is measuring in a minute how many times that you rotate. That's what angular velocity is, okay? So the formula that we use, first thing you want to know is we use the Greek letter omega to represent the angular velocity. We use theta to represent an angle, and then t is time. So revolutions per minute is a measurement, but in this formula, we're really talking about, in radians, what is the angle that it turns through in a unit of time? Okay, so if you've been wondering why angles need to be bigger than 360, well, here's one reason why. Because in a unit of time, if you're up to 4,000 RPMs, you're making a lot of revolutions in a minute, right? That angle is way bigger than 360. You see what I mean? Okay? So when you're dealing with things that are turning fast, you're going to go through more than one revolution around the circle. So that's the basic idea then. Okay, I'm going to do this example too, then I'm going to open up an applet that'll kind of help you understand this idea. First of all, the units for angular velocity, I want you to just write an example down. Typically, what we say is radians per second or radians per minute. That's usually the way we do this. RPM is also okay. One of the things we're going to learn how to do is convert radians per second to RPMs and back and forth, because they both mean the same thing, but that's what we're going to be using most of the time is radians per unit of time. Okay? So what this question number 2 is asking, we're going to work this out first. What I want you to do is draw a circle, and we'll kind of represent everything of this problem saying. Okay? So what the problem gives you is it says you have a 20-inch fan blade. Now, when I make these problems up, I have to be clear. I try to be clear. Is that like the radius or is that the diameter? Because you could take it either way. I'm going to take this as a radius. So let's say that's the center of the fan, and then there's your fan blade, and that is 20 inches like that. Okay, that's a diagram that I want you to draw. Okay, and then it's saying that it's rotating at 2,000 revolutions per minute. Okay, so what we're going to do is find the angular velocity in radians per second at a point on the tip of the blade. So here's what you're doing in angular velocity. This is what you're measuring. You're measuring in a unit of time how many radians that thing turns. Okay, and if it's going 2,000 revolutions per minute, that's a real big angle, right? Okay, that's 2,000 revolutions. Okay, so we're going to do that. So what this is this is real important, and to me this is one of the whole keys to the section is if you're given, this is worth writing down, if you're given RPM, then that means that you were given the angular velocity, okay, because that's what that is. Anytime that you're given revolutions per minute, then you have been given the angular velocity. Okay, that's the part of the section sometimes students overlook. So I'm wanting you to find the angular velocity. Well, I already gave it to you, right? Okay, but what we're going to do is convert that to radians per second. So I already gave you the angular velocity. We just need to convert it. Does that make sense? RPMs is a measurement. If you're given that, that's an angular velocity. If you were given radians per second, you would know based on the units that that's an angular velocity. That's a real key. So let's write this down. Let's just write down omega is equal to 2,000 revolutions per minute, and then we're going to do a unit conversion. Okay, how many people have taken chemistry before? Is anybody taking it now? Okay, I bet some people are taking it now. One of the first things you learn in a chemistry class is how to convert units with what we call dimensional analysis. If this is new to you, it's pretty easy to learn. So the idea is going to be this. Okay, we want to end up with radians per second. Okay, so the first thing I'm going to do is I'm going to convert the revolutions to radians. So here's what you do. If you want revolutions to cancel out, then you're going to put revolutions in the bottom so they do mark out. And we want to end up with radians, so we're going to try to find a relationship between revolutions and radians. And that's the first thing that you learned in this class, like last week. What is 1 revolution equal to? 2 pi radians, right? So you would have 2 pi and 1 there. And that gives you what's called a unit fraction. These two things represent exactly the same thing. So we're going to have 2 pi over 1. You're going to multiply by 2 pi. The reason you do that is because now we have converted this to radians per minute. Does that make sense? Okay, so you're going to do that all the time. 2 radians goes with 1 revolution. I put revolutions in the bottom so it'll cancel out, because I want that to go away. Okay? Okay, what else do I need to do? I need to change the minutes to seconds. Okay, so if the minutes are in bottom, then if I want them to cancel out, I need to have minutes on top so that they will cancel out. And then I want to end up with seconds. So again, you just do the connection. So you already know the connection, hopefully, is 60 seconds is the same as 1 minute. So that's your conversion factor. So we're going to write that down. Just 1 minute goes with 60 seconds like that. Now what I'm going to do on this primarily is just use the calculator to get an answer. I'm going to get pi as an answer, but then I've got to use my calculator. Okay, so I'm just going to multiply straight across. 2,000 times 2 pi is 4,000 pi. And then I've got 60 seconds like that. And again, my answer is in radians per second. And then you could reduce the fraction. If you reduce the fraction, you would leave pi in the answer. So let's go ahead and just calculate this out on the calculator and round this one down, okay? And that's what you're going to do most of the time, is just get decimal answers. So I'm going to go 4,000 times pi, and then divide by 60, and then I'll round that to like maybe 1 decimal. So that's going to give about 209.4 radians per second. Okay, so really that problem was nothing more than doing a unit conversion. Okay, that's the idea. So tell me if that makes sense what I did. Okay, now be comfortable with how to change these things. So typically you'll change revolutions to radians and minutes to seconds and stuff like that. That's the most common thing you're going to do. So that would be what that is. So what that's saying is that you're going 2,000 revolutions per minute. That's the same thing as every time a second goes by, it's 209.4 radians. Now that's fast, isn't it? Because 1 radian is 6.28. So that's like super fast, okay? That's really an engine that's cranking there, okay? All right. All right, so the next thing we want to do is we're going to do this problem a little bit different. Now what this says is, and we're going to see if we can kind of reason through this problem. I'm going to draw another circle here. And this time what it says is we're going to find the angular velocity, again, in radians per second, and the point's going to be 5 inches from the tip of the blade. Okay, so that's a 20-inch radius still, but you're going to be like 5 inches away. So what I'm saying here is we're here. Instead of at the edge of the radius, we're here. Okay? And what we're going to do is find the angular velocity there. All right? Now, let's think about what this would be. What does angular velocity do? Okay, it measures how many rotations that's going to go in a unit of time. So I'm going to ask you a question. Is it any different? What do you think? Make up your mind. I hear some people saying no, some people saying yes. Okay? If you don't understand why, I'll show you in a minute. It doesn't make any difference. So what's going to happen is we're not measuring the distance that thing's going. This thing is going a shorter distance, right? But what we're representing is how many times does it turn in the same unit of time. So like if you have a bicycle and a spoke, the spokes are going to rotate at the same rate, right? They have to. Because if they didn't, the spokes wouldn't stay rigid, okay? So the answer is it's the same, okay? And I'm going to show a little video and a little snippet on this that'll kind of help you understand this. So it's the same answer, okay? It doesn't matter where you are, the angular velocity is always the same, okay? Because it's measuring rotations, it's not measuring a distance, okay? So which part of the blade has the highest angular velocity? It doesn't matter where you are, okay? So it's always going to rotate at the same rate. Even if you're like right here, that thing is going to rotate at the same rate as it would anywhere else, okay? The only place it's different is right in the center where it's going to look like it doesn't rotate at all. So that's the idea. Does that make sense? Okay, if you don't understand this, I'm gonna do this. So I was looking for videos on YouTube. I like this one. This kind of is the best thing I could come up with to explain that. I don't know if you guys will be able to see this or not. Can you see the record player? You know what a record player is? Okay, it's kind of an old thing that we had when I was young. We didn't hit CD, it's not a CD. So there's 2 mock dolls on here. Aren't they rotating at the same rate? Okay, I mean, one doll's not getting ahead of the other one. So that right there shows me that angular velocity is always the same. How about you? Okay, now I'm going to show you one other thing that I found on the internet that I also think is kind of a good description of this. And we're going to get into this a little bit later today. So this kind of shows how pulleys work. So I'm going to go ahead and show this to you. So this is, think of like you have a bicycle sprocket. Okay, now what this is going to measure is this one's clearly bigger than this one. So the angular velocity is going to be measured for you automatically. So one of the things I want to show you is a little bit different concept on this, is I'm going to start this, and then I want you to watch the angular velocities. W1 is the angular velocity of the big circle. W2 or omega 2 is that, okay? So I want to show you a couple of things that you want to make sure that you understand on this problem. All right, so notice if you do this, the angular velocities are different. Can you tell that this one is turning faster than that one by looking? Yeah, okay, it has to. And the reason it has to is because basically this thing is going a longer distance, right? This thing's going a shorter distance. So if that thing is going to keep up with that, it's got to turn at a faster rate. Okay, and let me show you what happens if I do this now. Now I can adjust the radiuses. I can make these two things so that they're exactly the same size, or at least get close enough to show you. Okay, now can you tell they're rotating at the same rate? Okay, the reason is because they're the same size. So what's going to happen is your angular velocities will always be the same if those things are the same size, but if you change the size, the smaller one's going to start rotating faster. So that's kind of the idea. So if I did this, if I made this circle real big and made that one real small, like you can't even see on that if I do that, okay, now you can pretty clearly tell that the little one's traveling faster. Okay, that's the idea. All right, does that make sense, what I'm saying? Okay, all right. So that's going to be an important part as we go a little further in the section, that you understand that concept and understand it well. Okay, so let's go to the next thing I want to do is this problem number 3. And this is a real simple thing. This says you have an engine that's turning over at an angular velocity of 2,400 RPMs. I didn't have to say angular velocity. You would need to know that because I gave you RPMs, it is an angular velocity. Okay, so omega is the variable. So write down omega equals 2,400 revolutions per minute. Okay, and what I want you to do is change this to radians per minute. Okay, and all we got to do is just one thing on this. We already have the minutes, so what we should do on this is just make the revolutions go away. I did this on the last problem. Let's see if we remember that. So if we want to end up with radians, that's in the numerator, and if we want revolutions to go away, you put it in the denominator. Okay, what's the connection? What do you use for radians and revolution? What's the connection? One revolution is what? 2 pi radians. Okay, that's what we call a unit fraction, and you want to make sure that you put the numbers in the right place. Okay, so now our answer is in radians per minute. Okay, if I went through and kept pi in the answer, if I do 2,400 times 2, that is 4,800 pi radians per minute. And then you could take your calculator if you were directed to. I'm just going to stop the problem there. Okay, so make sure that you understand how to do conversions with revolutions and radians, because you're going to do that throughout the section. Okay, all right, any questions? Okay, now we're going to push on with this, and one other thing, then we're going to get a little bit into linear velocity. So I want you guys to go ahead and do the next one. I'll get your question in just a second here. So I want you to just write down 900 radians per second, but this time what I want you to do is change this to, and actually let's go to revolutions per minute. Scratch that and make that revolutions per minute. So see if you can do that. Takes like, you can do it all in one step, but there's 2 conversions that do that then, okay? So see if you can do that. And what you have to know basically again is 1 revolution is 2 pi radians, and you have to know the minutes and seconds, okay, which I assume you know. And we'll kind of compare answers to see if we're on the right track, and we're going to look a little bit at the idea of linear velocity, which is a different idea. Now, if this dimensional analysis is new to you, because a lot of times it is for students in the class if you have to take chemistry stuff, I want radians to go away, I want seconds to go away. Okay, so that's how you know how to put stuff in there. And let's see what we'd have on this. So for revolutions, you would have 1 revolution goes with 2 pi radians. So you got to do that. Okay, and then now the radians are gone. Now we got to do the seconds. So the connection is 60 seconds go with 1 minute. Okay, so that's what you should do on this. Now, I'll tell you, a lot of times students don't do this right on the calculator. We're going to round this to the nearest hundredth, so there's one thing you want to pay attention to. If I multiply the numerator out, 900 times 60 is 5,400, and then the denominator is just 2 pi. Okay, so you're going to end up now with revolutions per minute, or RPMs. Okay, now I'm going to do something like this, and I see students do this all the time in this class, and you got to pay attention to it. I'm going to do something wrong and see if you can tell me what I'm doing wrong. Okay, so I'm going to do 5,400, and then I'm going to divide, or was it 54,000? I think I'm missing a 0, aren't I? Yeah, okay. Okay, so I'm going to do 54,000. Come on, I'm going to put this in right. 54,000, and then I'm going to divide by 2 pi. Okay, and students give me that answer all the time. What did I do wrong? Because that's not it. I didn't put it in my calculator right. What did I do wrong?
You divide 54,000 by 2 and then multiply it all by 5.
Well, that's what the calculator did, okay, but that's not what I want to do. See, what this is doing is it's doing order of operations. When you multiply and divide, you go left to right. And what the calculator is doing is it's doing, like you said, 54,000 divided by 2 multiplied by pi. I don't want it to do that. I want it to do 54,000 times 2 pi. So I need to have that 2 pi in parentheses. Okay, you need to make a note of that because I don't want you guys making mistakes on stuff like that. So the correct way to put this in your calculator is 54,000, like that, and then divide by parentheses 2 pi. Because see, you have to control the order that the calculator is going through. So you want the calculator to do the 2 pi before it does that division. Now, if I do this, this is the right answer. Okay, so that answer of the problem would then be 8,594, and I'll round that to 2 decimals, so that's 37, and you can put RPMs on that for revolutions per minute like that. Okay, does that make sense why I put the parentheses around the 2 pi? That's a big deal. Pay attention to that. Good rule of thumb. If you're putting in a division problem in a calculator, numerator in parentheses, denominator in parentheses. That's a good rule of thumb to follow. Okay, so that's the idea. Okay, so that'll kind of get us through the idea of angular velocity. Next thing I want to do is introduce you to linear velocity. Okay, so if you're driving in the car, linear velocity is measured by your speedometer. Now, what we're doing in this section is we're only looking at motion in a circle, okay? So it's the same idea. So actually what the speedometer is measuring is it's actually measuring like a point on the edge of your tire and how far it goes in a unit of time. And that's totally different than angular velocity. Angular velocity is how many times it turns in a unit of time, whereas linear velocity is a distance over a unit of time. So the idea is this would be like in miles per hour or kilometers per hour and so forth. So what we do is we use V for linear velocity. That's the variable we use. S is the arc length. We already learned about that tonight. And T is time. So what we're really doing is we're doing the arc that it goes through in a unit of time. So what the speedometer is measuring is really like in a second, how far does a point on the rim of that tire go? What is its distance? So it's literally a distance over a time, okay? So that's what your formula is there. Okay, now the next thing I want to do is this is the formula that you're going to use the most often in your homework in this section. And what this formula does is this relates linear velocity to angular velocity in the radius. So in other words, if you know the angular velocity in the radius, then it's easy to convert that to linear velocity. Or if you know the linear velocity in the radius, then you can find the angular velocity. So you're going to use that more often than any of the other formulas in this section. Okay, that's pretty important. So let me do a little derivation of this. The derivation of this is actually real easy. So let me do the little proof of this. So go ahead and write down V is equal to S over T. Okay, that's the general formula for linear velocity on a circle. It's the arc it travels through in a unit of time. Okay, what did we learn like 10, 20 minutes ago about the formula for S? What was that? S equals what? R theta. We're going to replace that S with R theta, so you want to go ahead and do that. Okay, so this is now going to become r theta over t. Okay, now what I'm going to do is I'm going to circle this, and I also, on the previous page of the notes, it tells you what this is. Do you know what theta over t is? It's the angle something turns in a unit of time. Isn't that angular velocity? That's what that is. The angle in radians over a unit of time, that becomes omega. So you've got r, and then you replace what I circled with omega, and then you got the proof. That takes 2 steps to put that together. So what we'd get is the result, V is equal to R omega, okay? So that would be the idea. When you're working with these formulas, you're always dealing with radian measure also if you're dealing with any of the angles, okay? Okay, so let's kind of formalize this. One thing that you want to do is make sure that you understand the difference between the two. The simplest way to do this is angular velocity in your car is the tachometer, right? RPMs. Linear velocity is like the speedometer. It's a distance over a time. So you want to be real clear in the difference between the two and how the units go. All right, so let's solve this problem number 6 and see if we can put these together. Some of these problems will get a little bit more complicated as we go once we learn this formula V is equal to R omega. Okay, this problem is going to say the minute hand of a clock is 10 inches long. This one doesn't have anything to do with velocity. I don't even know why it's in here, but we need to go over it because it has to do with something we learned in this section anyway. So it says, how far does the tip of the hand move in 12 minutes then? Okay, so we're looking at a distance on this. So what I'm going to do on this is just sort of draw like a circle, and we're going to just see if we can figure out this distance on here. So it's a lot of times when you're doing a word problem, it's a good idea to draw a circle. Okay, so it looks like the minute hand is 10 inches long. We're going to look how far it goes in 12 minutes. So here's what would happen. Let's just keep it simple and say that's 12 o'clock, okay? That's your 12 on the clock. And then let's say that's 1, that's 2, that's 3. And then you're at 12 minutes like that. Okay, so that's what you're interested in, is you're interested in the distance from there to there. Okay, that's what you want to do. Now that is an arc of a circle, right? So that right there would be S. And if you're going to find S, what's the formula? S equals R theta. We do have the radius. The radius, we're just going to treat that as the length of that minute hand like here. Okay, so what you're going to do in this problem is you're going to do this. Okay, your radius is going to be this right here. So the radius is 10 inches. Okay, theta is this number right here. Now I didn't give you theta, but I gave you enough information to figure it out. Okay, this is just kind of a thoughtful problem. If you can figure theta out in radians, then you'll have it made. Okay, well, let me ask this question. What if it was from 12 to 3? That's obviously 90 degrees, right? What if it was from 12 to 1? What's that angle there? 30, right? Okay, if you go around the clock, that would be 30 degrees, 60 degrees, 90 degrees, and so forth, right? Okay, so every time that you're between 5 minutes, that's a 30-degree angle, right? But what we know is we know how many rotations we've gone through. So the way I'm going to think about this is like this. Okay, what I've done is theta is really this. It's gone through 12 parts of 60, right? Okay, so it's gone through a fractional part of a whole rotation of a circle. I'm using 60 because obviously there's 60 minutes in a hour. Okay, no, 60 minutes. Okay, now I'm confusing myself. Okay, so that's 12/60ths. Now we're going to convert that to radians. So how many radians are in the whole circle? 2 pi, right? So if we just take that and multiply that by 2 pi, you will have the radian angle on that. If you look at this in degrees, that's a little bigger than 60, isn't it? Okay, but we need to use radians when we're using this formula. So what I'm going to do is it's gone through 12/60ths of a rotation times 2 pi. Okay, now I'm going to just work this out and reduce the fraction. So that will give me 24 pi over 60, and then I'm going to reduce it. You can also change this to a decimal because we're going to have to do that anyway. But what I'm going to do on this problem is leave pi in the answer before I change it to a decimal. So I can reduce both of these numbers by 12. So 24 divided by 12 is 2. 60 divided by 12 is 5. So that means that that angle is 2 pi over 5. Okay, so what we have then is theta is 2 pi over 5 radians, and r is 10 inches. So if we want to find that arc, which is the distance the minute hand traveled, then we just do S is r theta. So r is 10 inches, and then I'm going to multiply that by 2 pi over 5 radians. And then again, we can reduce, okay? You can multiply out first, then reduce. So if you want to do it this way, you could. If you go straight across, you would have 20 pi over 5. So that would divide out to 4 pi inches, okay? So that would be an answer. Now you could take your calculator. So if you did 4 times pi, you would get approximately, I'm going to round it to 1 decimal, so that's like about approximately 12.4 inches, okay? The part of the problem sometimes students struggle to figure out is that 2 pi over 5, okay? And again, all we've done is we've gone 12/60ths around the circle. And that's really 1/5, okay? If you reduce 12 over 60, it's 1/5 of the way around, right? Does that make sense to everybody? Tell me. That's the key, right there. So if you were doing like, if you were doing like from 12 to 3, then it would be 15 out of 60, right? And 15 out of 60 is a fourth, right? And you can tell that that's gone through a fourth of the circle. Does that make sense? Okay, all right, that's how I figure that out, is with rotations, okay? All right. Okay, next one's going to get back to the idea of velocities here, okay? So let's take a look and see what we have on this, okay? Now, one thing when you're doing these problems, it's a good idea to write down the given information and know the right variables. So this problem is saying you have a circle, and it has a radius of 12 inches, okay? Then it says you've given a time of 20 seconds, and then it's going through a central angle of 1/4 of a radian. So we're going to do two things. We're going to find the linear and angular velocities or speeds, okay? So here's the way that I would attack this problem. First thing I would do on this is kind of what you want to do if you're in a physics class, is just kind of write down what you're given and know the variables. So we've got the radius is 12 inches, the time is 20 seconds, and then theta in radians is going to be 1/4 of a radian, okay? So I'm going to write down the formulas. The other thing is you got to know what formulas apply to that. So here's the formulas. First of all, we have for angular velocity, we have this general formula. That is omega equals theta over t. Okay? So do I have theta and do I have t? Yeah, that's how you would do the problem. Okay, you do that formula. Now, for linear velocity, which we also got to find, there's a couple of possibilities. The linear velocity, the formula is v is equal to s over t. Well, I gave you t, but I didn't give you s. I did give you enough information to find s, because s is r theta, okay? Or you can approach it this way. We also have this formula, v is equal to r omega. So in other words, once we find the angular velocity, then all we got to do is multiply by r to get that. So there's more than one approach to getting that linear velocity. So a good approach to the problem is write down what you're given, write down the formulas, and see which ones apply to that, and that'll help you kind of go through this. So the first thing we're going to do is we're going to do the angular velocity. Okay, so the formula we're going to use is omega equals theta over t, where theta is in radians. So we've got theta is 1/4 of a radian. And let's see, the time is 20 seconds. So that'll give you an answer in radians per second. We're just going to use a calculator on this. So that is 1/4 is 0.25. And it's okay to just give the answer in radians per second. If you're doing these problems like on my math lab, they'll tell you usually what they want, how to round and everything. So if I take 0.25 and divide that by 20, I'm going to get this answer. I'm going to get omega is 0.0125 radians per second. Okay, so just knowledge of the formula on that gets that answer very quickly, doesn't it? Okay, does that make sense to everybody? Okay, Now, if we want to find the linear velocity, well, the easiest way to do this is to use this formula. How come? Because we know that omega, but I also gave you r. So all you got to do is r omega, and then you'll have the answer to the linear velocity. So the second part of this, let's do that, okay? We're just going to do v is r omega. So the radius was given as 12 inches. Okay, the angular velocity was now we figured out as 0.0125 radians per second. Okay, then I'm just going to get my calculator out. Then I want to talk a little bit about the units on this. So if I do 12 times 0.0125, that will give me, I'm getting 0.15 on that. But I want to talk about, this is important you understand the units. There is no such thing as inch radians per second. Radians is not a unit. That's real important. Radians is a placeholder. Really, a radian measure is just a number. Okay, so just disregard the radians, and your answer is going to be inches per second. Okay, radians, think of that as a placeholder, not a unit. So the final answer on that would be 0.15 inches per second. In a problem like this, you might be asked to change to miles per hour, which you could do with dimensional analysis if you needed to do that, okay? All right, does everybody follow what I did on that, okay? Okay, now problem 8's probably the most challenging problem I'll teach you in this section. This one's got a lot of work involved in it, so we're going to go over this one, and this will take a little bit of space on your paper to do, because there's several things you have to know on this problem, okay? All right, now this one is going to go like this. You have, and really this is kind of like a sprocket. So what we're going to do on this is we're going to draw, let's start by drawing a picture. Okay, that's going to be a big circle, and then you're going to have a smaller circle, and just think like a bicycle chain or something kind of like that. Okay, and then we're going to draw like a little chain or a rope that's going around like that. Okay. And what we're going to do is this one has a diameter of 9. So the big circle, a diameter of a circle, is the distance all the way across the circle that goes through the center. Okay, and then the smaller one has a diameter of 3 meters. Okay, so that's the first thing that you're given is the diameter. So it's easy to find the radiuses, which you have to find. And then the other thing we have is the larger pulley rotates 36 times per minute. So the first thing you got to know as a student, in that statement right there, I'm telling you that every time a minute goes by, it goes 36 rotations. So what did I give you? What letter did I give you? Is that an angular velocity or a linear velocity? That's angular. How do you know? Because of the units. It's really saying 36 revolutions in a minute. Okay, it's not saying revolutions, but the 36 times implies that, right? Okay, so I've given you an angular velocity. So what we're going to do is two things. We're going to find the angular velocity of the smaller pulley, and then we're going to express that angular velocity that we get in RPMs. So we have enough information. So let's do this. We want to kind of get organized and write down what we have. So let's write down, kind of divide our paper up into two parts. We got the big, and then we got the small circle like that. Okay? Now, what we have is the radius, and I'm going to use a subscripted variable. I'm going to say the radius of the big circle, and a radius is what? If the diameter is 9, what's the radius? 4.5. Remember, a radius is half of a diameter, so that's going to be 4.5 meters. Okay. The other thing that I've given you is the larger pulley rotates 36 times per minute. So remember, that's omega. You would have to know that I gave you omega. Well, let's just write that down as 36 revolutions per minute for now. Okay, so those are the two things we're given. As far as the small goes, the only thing that we're given is the radius of the small circle would be half of 3, so that would be 1.5 meters like that. Okay, now what we're trying to find is the angular velocity of the smaller pulley. So ultimately, this is what we want to find, is the angular velocity of the smaller pulley. Okay, so here's kind of what you have to do in this particular problem. I've given you enough information to do this, but before I do anything else with this problem, I want to pull this off a minute, and I want to go back to that applet that I found on the internet, because this really should explain how this works, okay? And we talked a little bit about this earlier in class. So let me see if this thing will do this. Okay, so here's what I'm going to do. This is kind of the situation we have. All right, and this is what you have to understand. We talked about the angular velocities are different, okay, because the smaller thing has to go faster to keep up with that. But the linear velocities are the same. So here's what I mean by this. This red dot is going to represent a linear velocity, and it's always going to be the same. If you crank your bicycle, you're pedaling, that thing right there is always going to go at the same rate. Like if you pedaled at the same rate, that thing is not going to change, okay? So I'm going to do start on here, and what you need to understand on this problem is this concept, and this should show this pretty easily. The angular velocities are different. That one is slower than that one as far as rotational speed. The linear velocity is that red dot. Isn't that always going the same meters per second or whatever? That red dot's not speeding or slowing down. So in the problem we're going to do, the linear velocities are going to be the same. They have to. That's what you have to do in order to do that problem. And it doesn't matter how I change these radius. Okay, like if I do this, notice that no matter what I do, the linear velocities are going to stay the same. Okay, that's the key to this problem. Okay, does that make sense? Angular velocities are different, but linear is the same in that situation. So if we go back to the problem then, what we want to go ahead and do is let's go ahead and work with radians. You've got to work with radians, so we're going to go ahead and we're going to convert this thing like this. So we're going to go ahead and do 36 revolutions per minute, and we're going to go ahead and change that to radians per minute. Okay, so we need to work with radians when we're doing this. Okay, so I'm going to do this. I'm going to multiply by a unit fraction, changing this to radians per minute. Okay, like we've done several times in class tonight, 1 revolution is 2 pi radians. So if you multiply that straight across, the revolutions are going to cross out. So I'm going to end up with the angular velocity of the big circle is 72 pi radians per minute. Okay, so we got that. All right, and you do have to do that before you can do anything else in the problem. So the next thing I'm going to do is I'm going to do the linear velocity of the big circle. Okay, now we learned the formula a few minutes ago, and that formula goes like this. First thing I'm really going to do on this problem is V is equal to R omega. Okay, so see, I already know R, and now I know omega, so I should be able to easily find the linear velocity. Okay, so I'm going to write this as the linear velocity of the big circle is the radius of the big circle times the angular velocity of the big, like this. So let's do that. Okay, so what I'm going to have is the radius is 4.5 meters. Okay, the angular velocity is 72 pi radians per minute. Okay, and then I'm just going to take my calculator and work that out and see whatever 72 times 4.5 is. Okay, that's going to give me 324. What are the units on that? So I have a meter radian per minute. What did I say about radians a minute ago? It's not a unit, it's a placeholder. So my units are meters per minute. Okay, so right now what I have is I have the linear velocity is meters per minute. Okay, so I'm going to kind of keep track of stuff, and I got a pi in there too. And I'm just going to leave pi in the answer. So I've got 324 pi meters per minute like that. Okay, so that's what I've got so far. Okay, all right. Now there's kind of a chain of events here. So now I know everything about the big circle. The next thing I need to do, and if you were paying attention, you could tell me immediately what this is. What do you think the linear velocity of the small would be? The same, exactly. So that's the reason I did that, is because now I know this. Okay, they're the same. That's what I tried to show you in that diagram. So now we're going to know that these are the same. So I've got, I'm just going to write that as 324 pi meters per minute like that. Okay, so now we've got that. All right, now that leaves us with one more thing. Ultimately in this problem, what we're wanting to do is find the angular velocity of the small circle. So what that's going to imply is you got to use this formula. So the second thing we're going to do is use the formula V equals R omega again, but we're really looking at the small circle now. So notice that we know everything that we need to know now. So in this formula, we know the radius of the small circle that was given. We know the linear velocity. We figured that out. So we should be able to find the angular velocity. So what I'm going to do is solve this formula for omega. So I'm going to divide both sides like that. So what I'm going to end up with is, and I'm going to write this like this, omega, the angular velocity of the small, is found by the ratio of the linear velocity and radius, okay? So now we're ready to put everything together. So the linear velocity is this thing right here, okay? That thing was 324 pi meters per minute, okay? Then the radius on this was 1.5 meters, okay, like that. Okay, so I'm going to just take my calculator and I'm going to do 324 divided by 1.5. And we're going to work that out then. So 324 divided by 1.5 is going to give 216. Okay, so we got 216 pi, and then the meters cross out. Oh, hold on, I got a mistake on this too. Let's see. What did I do here? No, we're okay. I thought I was missing something on that, but I'm not. Okay, so what you have is you're really going to have radians per minute like that then. Okay, so we got that angular velocity then like that. Still doesn't seem like I'm getting what I thought I would get. So I've got 324 pi. That should be okay. Not. Oh, no. I know what I'm doing wrong. I'm doing nothing wrong, okay? What I'm thinking about is I want to show you how to make sense of the problem, okay? That is the correct answer of the problem. What I want to show you is this, okay? I want you to look at these two things right here. I was just looking at the wrong numbers because I already knew what the answer was going to be, and I'll kind of show you how I do that. Okay, this is the angular velocity of the small circle. That's the angular velocity of the big circle. Now remember, when I showed you that diagram, you would expect that thing to have a bigger angular velocity, right? Remember that diagram I showed where that little sprocket was turning faster? I'm going to ask you a simple question. What is the relationship between 216 and 72? What's the relationship between the diameters? That's 3 times bigger, isn't it? Okay? Check this out. That number is 3 times bigger than that. Okay? All that work to figure that. See, I knew that anyway. Okay? So what's going to happen on this is, if that's 9 and that's 3, this thing has to rotate 3 times faster to keep up with that. If that was 20 and that was 2, then it would have to go 10 times faster. You see what I mean? Okay? Yes.
So basically, it's just if you ask the same question over.
I want you to show everything behind this, okay?
You can just multiply it.
No, on your homework, I can't keep you from doing that. But I would like a student to go through that to understand the logic behind that. You'll see this on the homework, and now I've almost like given it away, okay? But I want you to know that relationship and how that works out. Yes, sir.
Wouldn't it be easier just to use, since we already had we had the 36 RPM, just put that in with the 4.5 to solve for V, A student.
Yeah, that would work also. I
It
think
seems a little simpler to me.
it's less work, it's less step. I think the reason I chose to do it this way is because I wanted to establish to you guys that the linear velocities are the same. So I was kind of thinking, okay, let's find the linear velocity, they're the same, and then compute it that way, okay? But now what you're gonna know is, you'll see a problem like this on your My Math Lab homework, that you will know how to do that in a different way, but this is the mathematics behind that, okay? Does that make sense what I did? Okay? All right, well, let's do one last thing, and then I'll finish up class here tonight. The other thing I wanted to do is let's do the angular velocity in revolutions per minute. So this is part B. We're going to do 216 pi radians per minute. We're going to change that to revolutions per minute. So again, we're going to get radians to cross out, and we're going to have 1 revolution goes with 2 pi radians. Okay, the pi's are going to cancel out, and then if you do 216 divided by 2, that should be 108. Oh, so 108 revolutions per minute. Okay, so that's just another way to write the answer. You can always write an angular velocity in radians per minute, and then that'll allow you to convert that to revolutions per minute like that. Okay, does that look good? Okay, so keeping this in mind, and I'll let you go here. So I think everybody's got onto this. I usually like to go through this to show you the relationship. So if you saw a problem like this, that was 10, and this was 2, and say that this angular velocity was 15, let's keep it simple. Let's say that was 10 radians per second. What would that be? Would be what? What? You didn't get John. Oh, hold on, that's a bad diagram. Let's say that diameter is 2. Okay? If that angular velocity is 10 radians per second, what is this angular velocity? 50. 50, because that's 5 times bigger, therefore that's 5 times bigger, okay? That's the simple way to do it, but you have to know the mathematics behind that, which is what I was trying to show you with all this work. Okay, does that make any sense? Okay? On your homework, try to do it that way, seriously. You need the practice of doing it that way. If you're going to take physics, which probably most of you are, then you want to run through that kind of like that, all right? Okay, so that'll finish this up for tonight. And then next time we just got a few more things to finish up. You want to be sure you bring 7.2 and 7.3. We'll finish 7.2. I don't know if we'll have time to get into 7.3 though, okay? And then the sections from here on out are going to go faster because the way our book's written is 7.1 takes a real long section. And then from here on out they're a little bit shorter and take about a class period to do one section generally. Where's your iPad thing? Oh, did you do? Oh, it is. That's that's your cover. That's some old book that you got from the library. I didn't even recognize that. That's a cool cover.
Alright. I'll see you there. Wednesday.
Or, we don't have another Zoom.
Have another Zoom this week?
Are they like once
I think it's 1 week for the first 2 weeks, yeah, and then I think it was gonna go to.
Like I was talking, so I won't be here Wednesday. So here is
Okay.
the homework.
Okay, I'll go ahead and take it.
I just had a question about.
Sure.
But I was thinking that would be a cool way to do meetings if you had. Everybody can.
This one, with this would be 6 and 8, right?
What is
This
doing
was
on the front? You're just changing
rounding,
that.
yeah, because they were all like around it. It would be 6, so it was 0.675. Okay.
Yeah, because you're just multiplying the 96 by.
Yeah, 96 would be is it.
Well,
So
you're
you just
multiplying-
multiply by pi.
Pi.
I did the fractions first.
Oh, okay, I see.
Yeah.
You're really multiplying by pi over 1/8.
Yeah.
Okay, that's fine. And then that's how that works.
Yeah, I just like working with the fractions.
Okay, that's fine.
But yeah, it's all done. And sorry, I was like 20 minutes late. I
Oh,
had
that's fine.
doctors, so I could bring a doctor's note.
Oh, don't worry about the late.
Okay.
Just, I just expect you to be on here on time most of the time. If something happens,
Yeah, it's just this week is
okay.
I had the because I
Okay, and you're not going to be here next time. So.
Wednesday. Yeah.
Okay, that's fine. So I'll be here. Okay.
Shouldn't be any more problems.
Okay, very good.
Okay. So Wednesday, I'm gonna be out of town.
Okay.
There's a writing assignment, the written assignment that I'll email to you. Is that
Yeah,
alright?
you can email that written
Okay,
assignment
and
to
then
me.
I'll get the notes from somebody.
Right.
Is that really?
Yep, you can do that. I'm gonna videotape I videotape tonight's lesson,
Okay.
then I'm gonna do the same thing Wednesday.
Okay.
Because I think
Perfect.
my videos don't start till like 7.6, because I
Okay.
started that, I think, in a previous semester, so you'll be
Okay.
able to get caught up from
Okay.
that. You ever had
Perfect.
Trig before, like in high school?
Yeah, except
Okay.
it was like math 1 and math 2.
Yeah,
Like, so
okay.
that's what they're called, so I don't really
So you
know.
learned SOHCAHTOA, and you remember that? That's what we're
Yeah.
gonna learn on
Yeah.
Wednesday night,
Okay.
is that kind of stuff,
Okay,
okay?
perfect. Thank
Okay.
you.
All
Have
right.
a nice night.
So should I bring anything in particular for Monday?
What's that?
Should I bring anything in particular for Monday?
No, okay, what, because, well, actually, next Monday's Labor Day, so we're not in class.
Oh, yeah.
So it'll be next Wednesday, and just go to Canvas and it'll tell you what to do. I think the only thing you have to do is,
The math
the
lesson.
second written assignment, which is on Canvas, and then the Mind Math Lab. Just go to Canvas and it'll tell you what's due and what you need to have for Wednesday.
Okay.
And if you miss you'll miss the lesson, so I'm gonna, see this thing, I made a video of this, so I post this like later tonight. And I'll do the same thing on Wednesday, I'll just do a video and post it on Canvas.
Okay.
And you'll be able to look that up if you need to, okay, get your notes that way.
Yeah, and
Okay.
you don't require a doctor's note, right?
No, you don't have to have that, because attendance is not really a part of the grade.
Oh,
It's just I am required to keep attendance,
oh,
and so there's no excused or unexcused, it's just do what you did, tell me you're gonna be gone, and
okay.
that's fine.
Yeah,
Okay, you're just responsible for keeping up with what you missed.
yeah. It's just, before classes, I was in Peru, and I got some sort of flu.
Oh, yeah?
Yeah, so the doctor was checking up on me.
Yeah, okay,
So-
that sounds good.
Yeah.
Yes,
Hi, so I accidentally missed class today. It was, I don't
you
know why.
accidentally missed class
Yeah,
today.
okay. This is it's not an excuse, but this is real life. Like, I don't know why, but I thought it started at 6. So my whole day I've had everything around 6. I have no idea why it's 6.
I'm pretty clear you'll never make that mistake.
I
again.
know, I like freaked out. I was like, cause I got here and I was like, weird, there's a class in here. So I'm like waiting and I'm like 30 minutes have gone by and I'm like, oh my gosh, what's my class working
Okay,
now?
so,
So I have the paper done. I'm
Have you
so
turned that
sorry.
in?
That was so
Okay.
irresponsible.
okay, just,
And then I'm getting the notes from another student and
Okay.
I'll look it up on campus.
yeah, there will be a video, because I went ahead and did a video, I just recorded tonight, so you're in luck.
Okay,
So
cool.
you can go home, and now it will be later tonight when I post it, because it
Yeah.
takes like 30 or 40 minutes for that thing to go to YouTube.
Okay,
And then when I do, there'll be a link on there, so, and you probably wanna watch it, because the material we did
oh,
on this is harder
I,
for students to learn on their own,
okay,
okay? But you'll be able to catch it, just look at the video and get your notes, and you'll be okay. And I know you'll never make that mistake again.
it was the weirdest thing. Like, I was like, what is happening?
That's okay.
I like wanted to cry. I'm like, why did this just happen to me?
Beginning of the semester stuff, and you know, that happens.
At
I'm
least I was
probably,
honest.
yeah, you're honest. I probably did the same thing when I was in college.
Okay, well, thank you
But
so
you got
much.
everything turned in, so you're fine, okay?
Thank you so much for accepting that.
All right, you're welcome.
Have a good night.
Ahora no me voy a universidad, no me voy. Esa es el final. No me voy.